Yo! What's up everyone? This is Bytor, according to the latest BuzzFeed poll. We are so excited to present the brainchild of one of our team members. As part of our holiday break, we were brainstorming how to provide additional value to the community. It is our goal to prepare you for your interviews. However, we realized not everyone has access to the same kind of education. Some educational programs may be stronger than others. Therefore, we decided to remaster a free online course that the team believes is one of the best IC design courses for analog engineers. This will not only help you during your interviews, but will also help you in your professional career. We would like to emphasize that we did not come up with this content, nor are teaching it ourselves. All the rights are reserved to the owners of the lecture. Before we jump into the course, we just wanted to thank everyone in the community, from our loyal viewers to our Patreons. You guys are the best. We do want to mention that it is our plan to release other remaster courses in other domains as well, provided they are not copyrighted. However, for the time being, we will be focusing on this course. That's because it takes roughly 6 hours between remastering the presentation, drawing, editing, etc. to produce less than an hour of video that you're about to see. We would very much appreciate it if you can support our work in Patreon so we can keep bringing you this amazing content. So let's not delay this any longer and let's start with the remaster course in Advanced Analog IC Design. We hope you enjoyed as much as we did. Cheers!
First things first, obviously, what is this class all about? Well, as I'm sure you guys know, this class is all about analog, but more importantly, this class is really about analog design, okay? So that's a little bit different than what you may have done in some of your previous courses, where a lot of the focus was actually on sort of analysis and understanding how things operate. That's still going to be obviously critical for everything we do here, but really the point of this class is to do design, okay? So typically the way that happens is there's some sort of set of specifications that you get. You go, you figure out some circuit topology that you want to use to meet that set of specs. And then you go and, you do the design, you basically come up with the sizes, you do bias currents, etc. And eventually, obviously, that has to go into layout, okay? So again, sort of in most even design courses, this is kind of the typical flow that you'll learn, and we will indeed cover that, meaning I hand you a set of specs and you just go and figure out how you build something that meets that set of specifications. But what we'll also do is actually look at where those specs even came from in the first place, okay? Because again, different than probably most of the sort of undergrad or maybe even grad level analog design courses you've taken in the past, the key point that I'm going to try and be making over and over and over again here is that you shouldn't just sort of take a set of specifications and implement them, okay? Because especially in analog, and this is true in design in general, but especially in analog, there are some things that are much easier to do than others. And by easier, I mean lower power or less design time or lower area or any one of another, a number of other metrics, okay? Now, the other sort of key point or really the goal that we need to get to in order to enable you to do that is to really understand how you create systematic approaches to doing analog design. Okay, and by systematic, I mean based on some set of fundamental principles where you can write out sort of a design document that says, okay, here are the steps I should take to get from point A to point B, and to tell me what are certain things going to cost. And again, cost could mean area, could mean power, could mean performance, etc. Okay? So really the goal is to enable you to come up with or to understand how would you create your own design methodology in a bunch of different applications. Because obviously there's no way that I'm going to be able to cover every single application that you might ever come across. Now, we will show you sort of a specific example of a design methodology that's been worked out, sort of over the years. And this is going to be for a relatively low-level component. So this will be for an operational transconductance amplifier, specifically being used in the context of some sort of analog to digital converter. Okay, so we'll use that initially to kind of drive a lot of the material that we'll talk about. But keep in mind, again, the point is really for you to understand how you'd come up with your own design methodology. So once we've done this, in order to really drive home the point about, look, there's a larger system that you're always working with, we're actually going to use a slightly more complicated sort of design driver that will really be part of our project in order to understand how would you yourself make some of these trade-offs that I'm going to be talking about. Okay? Now, the other thing that I should note, I'm going to be scribbling on the slides. Hopefully not scribbling, hopefully in a readable way, but I'll be writing on them. Okay, so as I mentioned, these are some of the sort of reference texts that we'll be using in the class. A lot of these are probably familiar to you if you've taken any analog design class in the past, which if you're here, you really should have. As I said in the beginning, this class is really all about analog ICs. Now, especially a few years ago, there was many people that would say, well, why the heck do we even have this class anymore? Right? I mean, shouldn't everything just be digital? And so why did people say that? Well, again, as I'm sure you guys have heard many, many times by now, there's that famous Moore's Law thing, right? And Moore's Law basically said, okay, if I scale technologies, then what it costs me to implement some function should basically go down by something like 30% each year. So just to put that into different terms, that means it's a factor of 30 every 10 years. Or more specifically, for those of you guys who are PhD students, it's about a factor of 5 during the time that you're here as a PhD. Okay? So if you're doing something that, isn't going to save you like a factor of 5, forget it. Just, wait for 5 years and then wrote, okay, I scaled everything, turn that into your advisor and get out of here. Okay? So why is this important? Well, what it basically means is that if I'm going to build something, if I can do it in digital, then really quickly it becomes very cheap to do that. On the other hand, in analog, that scaling is not quite as clear. Okay, so it's not as clear that the cost per function really does move along with the technology generation. And we'll get into sort of the details of why that is, but there's some really common complaints that people have about basically scaling analog into new technologies and why that's really nasty and doesn't actually buy you anything. So as an example, people will say, oh, the supply voltage is too low. I have horrible devices that have no gain at all. Like if I get a gain of 1, I'm happy. They match horribly. Like I can't rely on anything anymore. All this long list of complaints about why it really, really sucks to have to bring analog into some state-of-the-art technology. Let's say, 45 nanometers or something like that. Okay, and so, as we'll see through the class, some of these things maybe are correct. Some of them maybe are not so correct. But basically, based on that, just, it was a very common belief to say, look, analog's just going to die. Everything will be digital because digital eventually will just scale and it'll be so much cheaper, so we'll just go with digital. But actually, I would even claim that even if you believed that everything was going to be digital, you still need analog designers. Okay? And so why do I say that? Well, I actually claim that if you want to be a good digital designer, you actually have to understand analog. Okay? And so here's the way I make that claim. Well, in digital, sure, I can kind of push a button. I can write some VHDL and push a button and synthesize, some sort of fairly large circuit in the so-called ASIC flow. And I can get that to run at, let's say, medium frequencies, where medium maybe means like, about a gigahertz or so these days. But remember, somebody actually had to build the standard cells that you used in order to create that ASIC, right? So I kind of claim you need to know a little bit something about transistors to do that. Now, by the way, if you actually look at any big digital circuit, a lot of that is actually going to turn out to be memories. And so, in fact, if you say, okay, fine, maybe this is just a good digital IC designer, actually, if you look inside of memories, you really need to even know like a lot of analog stuff to actually get memories to actually work correctly. Now, it's actually even stronger than that, because if you really start pushing the limits on what you can do in digital, a lot of the issues turn out to really be analog. Okay? So just as an example, if you use some more aggressive circuit styles, there'll be things like charge sharing you'll run into. There'll be things like interconnect parasitic that will come into the picture, things like coupling. All these things that, even though we're dealing with digital, actually are basically analog issues that you need to know about. Okay? The other thing which is actually sort of a bigger and bigger deal these days is, as I mentioned before, no two transistors really match each other all that well, particularly in these more advanced processes that people are working with these days. And so again, even if you're doing digital stuff, particularly in things like memories, actually you have to worry a lot about just how the analog characteristics are changing, because if it changes too much, you might not actually get back something that's really digital the way you wanted it to be. Okay? So, first of all is just, okay, let's concede or let's argue that maybe the world goes digital. Even if it is, you still need to know analog stuff. Now, interfaces always turn out to be a little bit tricky, right? Because the world is analog. So actually, it turns out, even if you look at interfaces between two digital chips, and I really mean two purely digital chips, even there, actually, analog turns out to play a pretty critical role. So what I'm showing here is just a picture of, again, these are two totally digital chips, and we'll see if somebody recognizes where they're from in a second, that basically are just, see, if you can kind of see all these little traces here on the PCB, that's just a bunch of wires connecting those two chips together. So that's basically just the high-speed interface between them. So it's just sending bits from point A to point B, okay? So obviously the purpose here, at least on, let's say, the receive side of one of these things, is to figure out, were the bits that were transmitted on the other side, were they 1 or 0, okay? And so again, as it's going to turn out, and we're going to see this later on in the class, because this is going to be our driving example, if these are sort of the shape of the bits that I sent at the transmit side, by the way, this is called an I diagram. Literally all I did was just took all the bits that were transmitted and folded them on top of each other in time. Okay, so if you had something that was really perfect, you just see sort of things that look kind of square like this. And obviously, once you round it off a little bit, that's why it looks a little bit more like an I. Okay, but basically, you've got, nice, clean ones and zeros. The time when you get a 1 and 0 is also pretty well defined. So if that's what I transmitted, well, unfortunately, by the time it gets across that PCB, it looks more like what I drew on the right over there. Okay, so again, the point is now, well, I have a little bit of separation between the 1 and the 0, but it's not as clear anymore. Right? In fact, even the time at which it's a good digital 1 or 0 is also not all that clear anymore. Okay? In other words, I used to have this nice, clean digital waveform. Now it looks a lot more analog. Okay? And again, as we'll see later on in the class, I can actually take this really ugly thing, and if I pass it through some fairly simple analog circuits, I can actually get a very nice, clean digital bit back. Okay? So even if I'm talking about purely digital interfaces, analog actually comes quite a bit into the picture. Now, by the way, anybody have any idea what this, what PCB I happen to take this particular snapshot from? Anybody recognize anything here? It's the PlayStation 3. All right, so again, the sort of peak of digital stuff that you might be doing, this is your digital gaming machine on your digital TV, right? Actually, you've got quite a bit of analog buried inside of there. Okay, so we'll come back to that particular example just because, I happen to work on that one, so I know a lot of stuff about it. So, I can tell you more about that later, but that's why I happen to pick that particular example. But again, just about any other PCB you take, even like your laptop or whatever, similar type of stuff going on. Okay, so now, as people already pointed out to, I was kind of leading you in this direction of interfaces. Well, again, the real world is analog, right? And so, if I want to interface to just about anything, I basically need some sort of analog circuitry, or at least some understanding about what the analog behavior really is going to be. Okay? Now, by the way, just as kind of a reminder, don't forget that digital signals, of course, also have analog characteristics. In fact, the only reason we even invented digital in the first place was because there was certain analog characteristics that we kind of didn't want to have to deal with. We kind of wanted to just somehow ignore those or lump them into something. The key with digital is it's a way of building things that look like they have no noise in the system. Okay? So, again, if you look inside of most real chips, let's say that's what you thought your digital signal was. In reality, it usually does something like that. Okay? It's got all kinds of analog junk on it. It's just that as long as we build things that can reject that noise, we can kind of ignore the fact that a lot of that is happening. Okay? Now, by the way, again, even if you're doing mostly digital stuff, in many applications you'll work on, actually building the analog turns out to be sort of in the critical design path. So again, as if you look at, let's say, a microprocessor or something like that, there's probably about 1 billion transistors on that thing. Probably about, I don't know, let's say 990 million of those are digital, and about 10 million of them are analog. But those 10 million analog transistors took just as much time, if not even more, to design as the 990 million digital ones did. Okay? Because, again, it's analog. You have to worry a lot more about the details. So, just as a few examples, in case you don't believe me, we already looked at this. Just these things that basically talk from one chip to another, a lot of analog stuff inside of there. So that's anywhere from Ethernet to memory IOs. In fact, if you look at, let's say, big server systems with the optical interconnects, all that stuff has a lot of analog functionality inside of it. Another really, very common example of that is RF transceivers, meaning radios, obviously both on the transmit and on the receive side. We'll look at a couple of examples of that. And in fact, even sort of just in so-called sensors, this is maybe the most obvious one, a lot of basically analog processing that happens inside of there. And, just to stick with sort of the gaming example, the Wii and kind of all the cool stuff about the Wii, that's really just enabled by analog. Because there's this MEMS accelerometer inside of there, and that's really what's kind of driving all the coolness of that interface. So let's just maybe take a look at a few kind of examples for things. And in the process of doing that, maybe we'll sort of drive at why things are done sort of the way that they are. Okay? So let's look at an RF receiver in this particular example here. So what I've shown here is just kind of a block diagram of what a typical RF receiver looks like. Okay, and so you can see there's lots of stuff happening inside of here. So some sort of low noise amplifier, another low noise amplifier, some sort of filter, these mixers, basically a bunch of these various different blocks, right? So here's maybe just one kind of interesting question to, again, drive at why you might need to do analog stuff. So, okay, maybe the antenna, we said the real world is analog, so somehow I need to interface, with electromagnetic waves, so fine, I need an antenna, right? Just to kind of grab energy out of the world. But okay, why don't I just take that antenna and immediately afterwards put an ADC and then just process everything in the digital domain? Why don't I do that? Why, what's bad about that? Any thoughts? You need sensitivity, you need high sample rate, and if I combine those two together, it's going to be power. Let's put some numbers into this. So sensitivity, what does that translate into from the standpoint of an ADC? What's like the number that you would quote in terms of an ADC that would tell you the sensitivity? The number of bits. So anybody have any idea? How many bits would you need if you tried to do something like this? Depends on exactly what you're doing, but somewhere between about, let's say, 12 to 15 or 16 bits. How fast do you need to sample? Let's say I wanted to, build the radio that could cover every single frequency band that people are interested in these days. About what would that be? Any thoughts? About 10 gigahertz, right? In fact, there's probably about 10 gigahertz of spectrum that people are using, so I probably need about 10 to 20 gigasamples per second. Okay, so now here comes the fun question. How much power do you guys think an ADC like that would actually take? So just to give you an idea, well, maybe you can't do this so easily. If you took one of the, let's say, latest and greatest Agilent oscilloscopes, or actually even Tektronix or one of these other companies, and you opened it up, inside of that box is a about 8-bit 20 gigasample per second A to D converter. Okay? These days, those things take about 10 watts. So by the way, notice this was 12 to 15 bits, because we'll talk a little bit more later. Adding one more bit, unfortunately, is not just a factor of 2, but a factor of 4 in power. So you can calculate pretty quickly how much power you'd have to take if you really wanted to do what I said here. Now, that design that I talked about was, relatively old, so there's maybe some scaling factors you can apply there, but bottom line, it's going to take you something like 10 watts or so. So I don't know about you guys, but I don't want something dissipating 10 watts next to my head. All right, that's just too hot. No good for me, at least. Maybe on a cold day like this, it's a good heater, but other than that, I certainly don't want it. Okay? So that's really the problem. It's really that if you wanted to try and do that, it would cost you a lot of power. And so it turns out that if you actually do all this kind of complicated stuff that I've drawn here, you can actually do it in way, way less power consumption. Okay? So just still sort of sticking with the RF side, hopefully I've convinced you why you actually want to build some RF stuff. The other thing that's or really the other two things that are interesting to look at is, roughly speaking, there's about a 50-50 split between stuff that's quote-unquote RF, meaning operating up at some carrier frequency, versus the stuff that we usually refer to as quote-unquote analog, meaning it's down at baseband and has some bandwidth around that. The other thing that's kind of interesting to look at here is, this is a dye photo of a wireless LAN transceiver. And by the way, this was back in 0.18 micron technology, meaning relatively old technology. Even here, if you look at it, actually a large chunk of the dye is just taken up by RF and analog stuff. Okay? So again, if you didn't believe me before that, RF and analog from a cost standpoint is actually oftentimes fairly critical, just take a look at this picture. Because again, this isn't a pretty old technology. So if I move this to, let's say, 45 nanometers, all this digital stuff around it, I shouldn't say disappear, but, would look way, way smaller, right? Whereas a lot of this stuff over here, not so clear that it would actually change in size at all. Okay, so again, that's why kind of doing analog design turns out to be fairly critical. Now, by the way, just because this is sort of an issue that you, again, probably have heard about many times, I kind of notice how there's this, analog and RF stuff over on the corner, and then there seems to be some space around it. Why is that? Why might you do something like that? Why would you leave blank space on, the silicon die, which, by the way, from a real estate standpoint, silicon acreage is like the most expensive thing on the planet by many orders of magnitude. So why would you leave blank space? Basically, you're worried about, there's some digital, I'll be mean since I'm also a digital guy, there's some digital junk happening there, right? That digital junk can create noise or really interference that couples into the analog stuff. So again, as we'll maybe talk about a little bit more later on, one of the sort of simplest ways to just avoid that is just leave space between them, okay? So again, a lot of these sort of analog types of issues, even if you're sitting just next to some digital thing, actually turns out to be a pretty critical thing that you really have to worry about. So this is just another sort of typical example of where analog really comes into the picture. This is a MEMS accelerometer that Professor Boser had done, actually about, I guess that's almost 15 years ago now. So again, this is actually something very similar to what you might find inside of your Wii. So the idea here is that basically, essentially, based on some motion of a suspended structure, you're going to try and figure out how quickly is your chip actually accelerating. Now, what's fairly impressive is if you look at some of these sort of types of designs, the level of sophistication that people get to in terms of how good you do of a job from the analog standpoint is a lot of times these things are measuring displacements down in the sort of subatomic range. Okay, so to get the kind of resolution that you can do today, that's kind of the equivalent displacement you'd really be measuring. Okay? So again, the point here is that, you can try and do that kind of in a straightforward digital thing, but trust me, if you don't understand the analog, basically ain't gonna happen. Okay? So again, just to sort of wrap this up a little bit from the discussion about, digital versus analog and why we're even here in this class. In digital, really, again, the key thing was that I could basically abstract things as being ones and zeros. And again, the reason I did that was so that I can essentially say that for stuff that varies around the actual analog level, I'm just going to ignore that, right? And so that lets me say that I have a noise margin, lets me build things up and pretend that there was no noise in the system. Now, what's great about that is that lets me really abstract my design. It really lets me sort of ignore a lot of the details as to what's happening. And so because of that, I can basically say, okay, my abstraction is, let's say, either gates or registers. And so I can write some sort of hardware description language. And then based on that hardware description language, I can come up with all kinds of rules and techniques to essentially automatically generate my entire design based on that description. Okay? If you contrast that to analog, well, in analog, oftentimes the lowest level sort of abstract, or really the highest level abstraction we can do is the device. Okay? And unfortunately, it's usually like, the device model that's our abstraction. So by the way, how many of you guys have actually opened up a BSIM model and taken a look at it? Anybody ever done that? Okay, so I'm guessing at least a few of you have just opened like, the list of parameters, right? And if you did that, you saw there was probably about 300 of those parameters. Well, by the way, the model is several thousand lines of code, okay? So this doesn't sound like very good news from the standpoint of doing design, right? Because I don't know about you, but I can't think several thousand lines of code in my head, right? I can't use that as a very simple abstraction, right? So that's really one of the reasons why analog is just so much harder to actually do from a design standpoint. And to kind of phrase this another way, if I want to build analog stuff, obviously I'm going to have to do better than BSIM. I'm going to have to do some sort of abstraction. But the trick you run into is that the abstraction you end up using really depends on the context of what you're interested in. Okay? Because it may be that you're working, let's say, with op amps, and what you're doing makes a lot of sense for op amps, and so that's your abstraction. Maybe what you really want is a filter, so that's your abstraction. Or maybe what you really want is a comparator, and so that's your abstraction. In fact, actually, each one of these three things that I just talked about, I could actually implement in almost exactly the same way. And it's just based on the context of how I'm using it that really changes how I think about this particular block. Okay? The other thing, of course, is just from a design standpoint, analog layout usually is very meticulously handcrafted. And we'll actually talk some more about some of these sort of tricks and rules that you need to follow to do that. But very, very rarely is this ever actually generated kind of by you pushing a button. It's usually you sitting there and like, you move that little piece of poly, and you move the little diffusion, and you try and really craft it down to that last little detail. Okay? So, just in terms of what we're going to be really focusing on here in the class, our focus again is going to be really on analog rather than quote-unquote RF. And so just to sort of, not necessarily be mean, but just to sort of quantify what I mean by that, in this class what I mean by RF is essentially analog with inductors. Okay? So all that means is that in RF, basically you're usually dealing with things that look relatively sinusoidal, meaning they're relatively narrow band. They may be at a pretty high frequency, but the bandwidth around that frequency generally isn't that large. Okay? So because of that, you tend to use these so-called tuned circuit techniques. And by tuned circuits, that usually means some sort of LC resonant type of behavior. And so that's what I mean by analog with inductors. The other sort of big difference with analog versus RF is that in RF, the impedance you can actually use, meaning the impedance levels you use, unfortunately are often relatively constrained and are fairly low. Okay, so I kind of mentioned here that I can't make the antenna impedance too high. Anybody have an idea why it is that, in RF you usually end up with these fairly low impedances? So remember, all an antenna is doing is transforming from the impedance of free space to whatever it is that is inside of your system. Okay? So now, why might you want that to be relatively low impedance? What does low impedance kind of mean? What's bad about things with high impedance? So the problem is, if I have things that have high impedance, it's hard to suck power out of them. Okay? And remember, if I've got an electromagnetic wave, I want to suck power out of that thing, or at least absorb it into my receiver so that I can actually get the signal out. Okay? So the trick with RF is you usually end up with these pretty low impedances because you're really limited by the power of the signal itself. Okay? In analog, or so-called analog mixed signal, I have a lot more design freedom. So as an example, if I want to get voltage gain, I want to have really high impedance. Right? Because, if I have some transconductance and I drive a really high impedance, then I'll get a lot of voltage gain. Similarly, if I want to get current gain, then I'd have a relatively low impedance because I want to suck all that current out. Right? So really, again, the key difference here is that in analog, we're dealing generally with either voltage or current gain, but not power gain. Whereas RF, the reverse is generally true. Okay? The other sort of big difference is that in analog and mixed signal, oftentimes I don't deal with continuous signals, but rather with sampled signals or discrete time signals. Again, that's going to sort of translate into differences in the way we even just think about how our circuits are actually operating. Now, the other thing that's sort of interesting is that if you sort of look at some of the trends as to what RF has been doing, there's actually been somewhat of a shift towards more quote-unquote analog design techniques. So if you looked at, let's say, a sort of classic RF receiver, you can see there's lots of these inductors here, lots of tuning that, sort of gets it down into one particular frequency band. Well, again, if you remember actually from this dye photo over here, you can actually almost even see them. All these inductors are pretty darn big, okay? Because whether we like it or not, Maxwell's equations just, they're not changing, right? They're not scaling along with our transistors. So if I need a certain size inductor, certain physical size that I actually have to cover to do that, okay? So as we're scaling actually, and I've written what the technical details of that means, we're moving more towards these so-called analog types of techniques where I maybe have this fairly broadband amplifier. So now, again, I said I maybe wanted to do this because then I could get rid of a bunch of inductors. It's smaller. It's then easier to scale. So what's the penalty I paid? Why didn't people do this from the get-go? What's quote-unquote bad about that? It's noise. Okay? So the real reason why people did this was because even if you could get the thing to operate from there, as we'll see a little bit later on, if you make a circuit operate over a wide bandwidth, it's actually going to pick up more noise. Okay? So it's going to turn out the amount of noise that you'd be picking up is actually related to the device speed in some way. And so that's why this becomes more attractive as the devices are getting sort of faster. Because we're definitely going to pay a noise penalty, but maybe not such a huge thing so that we can actually reap some of the benefits of getting rid of these inductors. Okay? Now, so again, what we're really going to be focusing on is mostly these sort of mixed signal types of designs. And as I hinted at a little bit earlier, in mixed signal designs, actually, a lot of times it's really sort of difficult to figure out what the abstraction should actually be. And in fact, in many cases, it won't even be clear where's the line between what's digital and what's analog. Okay? And this happens very, very often in things that sort of straddle the interface between the two. All right, so analog to digital converters, that's kind of the classic example. But I've shown another example here, which is a so-called phase lock loop. So phase lock loop, just in case you haven't heard of it, all it does is it takes in some input clock frequency and generates another clock frequency, perhaps at a different higher frequency, but that just is locked as being some multiple of that input clock. Okay? So, if you don't know the details of what's going on in this block diagram, don't worry too much about that. The key point here is really, again, sometimes it's not even clear what's analog and what's digital. Because as an example here, what I'm showing is that maybe the way I generate that new frequency is by changing the supply voltage of some ring oscillator, right? If I ramp the supply voltage, the thing goes faster, right? So now here's the quote-unquote $1,000,000 question. Is this circuit here analog or digital? So, if I look at it inside of it, it's kind of a digital circuit, right? It's just a pile of inverters and, I can do all the standard digital calculations I do. Well, but I'm driving it from a port that has an analog characteristic, right? So from that standpoint, it's analog. Well, again, I don't know how to treat it unless I really think about what it is, the characteristic that I'm interested in, okay? Once I know that, then I can decide, okay, should I treat this thing as being digital? Should I treat it as analog? Bottom line, I really have to understand what it is that I'm trying to implement. So the last thing that I want to just briefly touch on, and we'll actually see this more as we go through the class, it used to be that sort of, in analog design classes, you really talked all about just analog and amplifiers and things like that. Well, these days, you can't really do that. Okay, you really got to think about, again, what's the overall system you're going to be in, and actually, what's the digital stuff that you're going to be talking to? Because even if you're doing a quote-unquote very traditional analog thing, there's probably going to be a lot of digital stuff wrapped around it. And the reason for that should be sort of fairly obvious, right? We said before, digital, from a cost standpoint, scales very, very nicely. So if I can figure out some way of building some digital stuff that makes my analog better, then actually oftentimes that's really the right thing to do. And actually in RF, this is one of the most obvious things because, as I'd mentioned before, inductors are pretty big. So if you actually look at it in 90 nanometer, one RF inductor, which is about, let's say, 200 microns by 200 microns, takes the same area as an entire microprocessor. And now, this is maybe not the latest and greatest microprocessor, but this is maybe equivalent of, I don't know, a 286 or 386 or maybe even a 486. Okay, so a fairly sophisticated thing, meaning a few million or at least a couple million transistors, right? I can do a lot of stuff with a couple million transistors, right? I can figure a lot of things out. So again, the point here is that when you can, it really does make sense to leverage some sort of digital processing to make your life easier in the analog domain. Okay, and again, we'll talk some more about what are the kinds of problems that you can solve very easily in digital versus in analog. Now, again, this is not to say that analog design goes away, or I should say good analog design, because again, if you really want to figure out what's the right, where you really draw this green versus white lines, or black lines, I should say, you got to understand what style of implementation makes the most sense in what context, and what really the whole system drives you to end up wanting to do. Okay? So that's really just sort of a quick overview of just why it is that we're even here in the class. In terms of the details, we'll start out with next lecture talking about kind of the devices themselves, really just to set up the things that we're going to be interested in. So we'll look at both passive devices and the active devices. And in fact, we'll probably spend more time on the passives, because in analog, that oftentimes is even more critical than the active devices themselves. And again, it's not that we're going to spend a lot of time on modeling, but we're really going to look at this in the context of analog designers and how we want to use those components. The next topic that we'll spend a lot of time on that you may not have seen in the past is electronic noise, because that's actually going to turn out to really set the power consumption of many of the blocks we're going to end up building. Once we've sort of understood that, then we're going to come back and kind of review some of the basic support functions that you've probably seen before. But now that we understand more about noise and some of these passives, we're going to sort of take a closer look at how you'd really want to do those kinds of things. So things like current sources, references, biasing, we'll take a look at that. Once we've got that in place, then we'll really start our sort of journey on looking at design methodologies. Okay, and again, the first sort of thing that we'll look at is the so-called, most basic analog gate or an amplifier. Okay, so we'll look at basically what type of methodology would you use to design that, what are the contexts in which you'd use that, how would you use it in, let's say, feedback, how does that usually translate into things when you look at discrete time response, things of that nature. Once we've done that towards the end of the class, again, to really give you a chance to exercise the material that you've learned and understand how to come up with a design methodology in a new application, we'll spend some time looking at basically high-speed links, meaning interfaces between two digital chips. And so again, that'll motivate sort of some additional building blocks as well as why we care about certain specs. But it's just going to give us a sort of driving example to really exercise a lot of the material that we've been talking about. And then if we have time, we'll talk about some other sort of components that usually end up being critical in many of these analog mixed signal domains, but we'll sort of see how things go and where we get to from that standpoint.